The next topic that we take is total internal reflection. Now, I won't introduce total internal reflection directly by a definition. Instead, I will first discuss the conditions for the situation for total internal reflection, and then we would like to make a definition, a formal definition for total internal reflection. So just imagine that there is water surface, a denser medium, and a ray of light travel from denser medium to rare medium, from water to air. Now, at the normal, this is angle of incidence. At this place, there are three possibilities. First possibility is that partly this ray of light will be reflected and partly this ray of light will be refracted. So, a part of this ray of light will reflect, and that part which will reflect will obviously be at an angle I, because it always follows angle of reflection. And the part which will refract, it is going somewhere here. I am showing it with a different color. It does not mean that its color will change. Just the difference is that it is, I am just showing it to just show that it's a different part which was refracted. So remember, color never changes. That's why even if I wanted to show it differently, I am using it the red color only. Now, in case, if from this situation, in a second state, the angle of incidence is increased. The angle of incidence is now increased for the same ray. For the same ray, in this new situation, the angle of incidence is increased. If the angle of incidence is increased, no doubt, there will be another ray which is reflected at the same angle. But on increasing the angle of incidence, at one particular angle of refraction will increase at one particular angle of incidence, which will be called as critical angle. We will observe that angle of refraction has reached to 90 degrees. So, what we have done is, we have increased the angle of incidence. Over here, if I show, we have increased the angle of incidence. On increasing the angle of incidence, obviously the angle of refraction have increased. And when the angle of refraction have increased, so in this situation, we can observe the angle of refraction is 90 degrees. And this angle of incidence is called as critical angle. C, it is represented by C. Now let's take another situation. And in that another situation, if I am replacing with this one as well as this one, so I take the third situation, and in the third situation, the angle of incidence is increased beyond critical angle. So it's a third situation where the angle of incidence is more than critical angle. So I take it now from here. So this is the third situation where the angle of incidence is more than critical angle. In this case, what will happen? Yes, obviously, that part of the ray which was supposed to reflect, yes, it will reflect. It will reflect at the same angle of incidence, which was more than critical angle. But what will happen to this ray? The ray which was earlier going into the rare medium has to come back into the denser medium. And once the ray is bouncing back into the same medium, it is reflection. And for any reflection, it has to follow law of reflection. That means even this ray, which was earlier going to the rare medium, is coming back to the same medium, and when it comes back to the same medium, it will reflect. And once it will reflect, it will follow law of reflection. It means in this situation, 100% of the light reflects. 100% of the light beam reflects. And this is total internal reflection. Total internal reflection. So if I ask you, what is total internal reflection? Why should we call it total internal reflection? So our answer is because it is this time 100% of the light beam which is going from denser medium to rare medium reflects back. It is not usually so. In usual condition, partly it reflects, partly it refracts. But in total internal reflection, it is 100% of the light beam which reflects. It follows law of reflection. That's why we call it total internal reflection. And then, if I ask you, what are the conditions of total internal reflection? If we just try to recall, what are the conditions of total internal reflection? So conditions are, number one, angle of incidence should be greater than critical angle. And second, the condition is light should go from denser medium to rare medium. So light should travel from denser medium to rare medium, and angle of incidence should be greater than critical angle. In these two situations, we observe total internal reflection, where 100% of the light beam reflects back into the same medium. Now, if we wish to make a definition for total internal reflection, the phenomena by virtue of which the light beam that travel from denser medium to rare medium tend to reflect completely into the denser medium. For this, the conditions are angle of incidence should be greater than critical angle, and the light beam should be traveling from denser medium to a rare medium. So the phenomena by virtue of which a beam of light traveling from denser medium towards the rare medium gets reflected back into the same denser medium at the interface of the two medium, obeying the law of reflection, is called total internal reflection. So now you are in good position to understand this total internal reflection, and then I can also make a relation of this critical angle with the refractive index of the medium. So if we wish to make a relation of critical angle with the refractive index of the medium, so we just recall the conditions. This light beam that was moving from denser medium to rare medium at angle of incidence is equal to critical angle. It was partly, you should never forget, it will partly reflect, and the other part of the light beam at critical angle would go along the surface. Now I would say, and this angle of refraction is this time 90 degree. So I would say W mu A, water to air, is equal to sin I by sin R. And when I say sin I is that critical angle and sin R is 90. So we have a final situation W mu A, water to air, is equal to sin C, or generally we are in a habit to write A mu W. So if I say A mu W, it will be what? 1 by sin C. Or we can also call it 1 by A mu W is equal to sin C. And then that's why we can write A mu W is equal to 1 by sin C. So if you know the refractive index of a medium, of a denser medium, you can always calculate critical angle. And that relation is A mu W, or refractive index of that denser medium with respect to rare medium, is 1 by sin C. So it is all available in the form of text. Critical angle is that angle at which the reflected part goes as it is, but the refracted part is making an angle of 90 degree with the normal. The conditions for total internal reflection, which is very, very important, the light should go from optically denser medium to rare medium. The angle of incidence, if you want total internal, this is not total internal reflection. If you want total internal reflection, then you will have to see that angle of incidence is more than critical angle, so that the light beam totally reflects here. So angle of incidence should be more than critical angle. Then relation of refractive index A mu B, or refractive index of, if this is medium A, this is medium B, then A mu B, or refractive index of denser medium with respect to rare medium, will be 1 by sin C. So that's how is total internal reflection. You will observe some very interesting numericals and examples on total internal reflection. So now, after learning total internal reflection, we can talk about some very, very practical, some very, very important applications of total internal reflection. There are so many observations in our daily life that are based on total internal reflection. Let's see the first one. It is total internal reflection in prism. In fact, if A mu G is 1.5, the refractive index of glass with respect to air is 1.5, then critical angle for this A mu G is, it can be calculated as 42 degree. So using this property, we can talk about the behavior of a right angled prism. Think of a right angled prism where two sides are 45 degree each. Now a beam of light is made to fall straight. So if the beam of light is made to fall straight, here the angle of incidence will be 0 and angle of refraction will be 0. So at this point, the beam of light will travel straight. But then it comes here. This is 45, so how much will be this? 45 degree. And if I assume a normal here, it is again going to be 45 degree. So this is normal, and it is going to be an angle of incidence 45 degree, and that angle of incidence 45 degree will be greater than critical angle, which is 42 degree. It means this light beam will reflect back, and this will reflect back at an angle 45 degree again. So this light beam is going to reflect back, and once it reflects back here, the angle of incidence is 0, angle of refraction is 0, so it will travel straight. And that's how you can see there is a change of 90 degree in the path of it. So with the help of right angled prism in this arrangement, you can change the path of the light ray by 90 degree. Now this is of good use. This concept is of good use in making short length telescope, that we will talk how do we make it. But the best part is that in this reflection, where you are changing the light path by 90 degree, you can use a mirror also instead of this. But in mirror, there will be some absorption and 100% reflection will not take place. But in the case of a prism, you get 100% reflection because it is a case of total internal reflection. So once again, I'm repeating, although you could have used a mirror here for this, but in that case, there will be some loss of light. But in the case of total internal reflection, there is no loss of light. No loss of light at all. So this was one example of prism. Now we take another example where the same prism can be used for change of path of ray, and that is, just imagine you have a prism this time like this. And yes, obviously it's a right angled prism. Now here, the light beam is made to incident normally like this through the base. Obviously, both the angles, both sides, it is going to make 45 degree and 45 degree. This is 90 degree. And this will be 45 degree and here is normal. So this is again 45 degree. Now this light beam, when it is traveling here, will suffer total internal reflection at 45 degree. And then again a normal. This is again going to be 45 degree because this is 45, this is 45. And it will suffer a total internal reflection here again at 45 degree like this. So the light beam is turned by 180 degree or pi. And here again it's a total internal reflection, so there is no loss of light. There is no loss of light intensity. If I try to compare with this figure, in this arrangement, in fact, the arrangement is so that the light beam was made to enter here. And from here it was reflected and then it is going back. So it is the same situation, just another point of view. And now we take this third case. In the third case, we can see what will happen to the size of image. So you have this right angle prism here, and maybe there is an object AB lying here. One ray will travel, it will reflect back. Again, it will suffer total internal reflection because every time this is 45 degree, more than critical angle, and it gets totally reflected. Now, in order to show it different, the ray from the bottom and obviously the rays from everywhere, they will also follow total internal reflection, and as a result, this reflected image that you get inverted, again turned by 180 degree. Yes, its size should be same, and that is not here because I could not make it straight line. So if you make it straight line, you will get the same size. This A dash B dash just inverted, it turns by 180 degree. So there are three cases, and a question can be asked in the exam, simple question. In a right angle prism, show how by total internal reflection you will change the path of the ray by 90 degree, by 180 degree, or you will get an inverted image of the same intensity. So very well within your reach, you could understand it well, and then some very important, some very usual thing that you observe, and it is mirage. You must have seen on the roads, when you travel on the road on a hot summer day, you will observe as though there is some water on the road, and when you reach there, there is no water. It's an optical illusion. And the same optical illusion takes place in desert. Maybe in desert, it is you who is standing and far off there is a tree. Then on the surface of this desert, it will appear as though some water is lying here. For water lets you blue color. So it will appear as though some water is lying here. And in addition, not only water, you will observe an inverted image of the tree. And that is mirage. So this optical illusion, this phenomena is called as mirage, where you either get the illusion of water at far off place, at some far distances on a hot surface. It may be sand or it may be a road. And also you get some inverted image of the object. You can get some inverted image of the car traveling on the road, and you can also get inverted image of a tree. Now how? It is due to total internal reflection. So over here, this picture, it is giving you a basic idea, and then we'll try to make it in a more detailed way. Actually what happened, that these layers of the air which are closer to the surface are hot, because the sand gets very hot as compared to the upper layers of atmosphere. Similarly for the road. So the lower layer of air, because the air gets very hot relative to the upper part of the atmosphere, over here we observe rare layers. So the hot air, it's a rarer one. I show this rare layers by more gap between the layers. And as we move up, the temperature is relatively low, so the density of air increases as we go up. So in these areas, you will find that air closer to the surface is rare, and it's a rare medium. And the air much above the surface, it's a denser medium. Now when a ray of light, it will travel from denser medium to rare medium, it tend to bend away. And again it tend to bend away. At particular position, you may observe the angle of incidence is greater than critical angle. And once it is there, it tend to reflect back. And that's why a person who is observing maybe somewhere here will observe as though the ray is coming from somewhere here. So the point is that the light ray, which is traveling from a denser medium to relatively rare medium, that has more and more angle of incidence, and it travel, and at one point it tend to reflect back completely. So there is a total internal reflection at one point. Angle of incidence is greater than critical angle, and thus there is a total reflection. And that's why the person observes as though the ray is coming from somewhere here or from somewhere here. So every part of this tree will have its own ray reaching to the person, and thus will have its own virtual image under the surface of that sand or road. So the basic idea is that the reason behind mirage is total internal reflection. And now we can talk about this total internal reflection in some more detail, as you can see over here. So over here, I'll try to make this tree. So it's a tree over here, maybe. So just imagine you have a tree, and then let's show the air layers. The layers of the air which are closer to the surface are rarer, and as we move upward, they are relatively denser. Now a beam of light which is traveling from here will travel from denser medium to rarer medium. It will travel a little far. Angle of incidence will be more than angle of reflection will be more than angle of incidence. And again, now the angle is increased. Now again, it is going from denser to rarer medium. It will travel a little more. The angle of refraction will be little more. And again here, when it is traveling from denser to relatively rare medium, it will bend more further. So every time the angle of refraction will increase. And maybe at this time, maybe at this situation, the angle of incidence which is here is more than critical angle. Now what will happen? The light ray will reflect totally. So if you are standing here somewhere, we imagine that it is you who is standing here somewhere. To you, it will appear as though this ray is coming somewhere from here. And it is not only for a ray traveling from this part of the tree. From every part of the tree, if a ray is traveling from here or from some other part, and as a whole, you will get an inverted image of the tree. Don't expect the tree to have an inverted image like this. It will have an inverted image like this. And that's why I made the tree leaves to be on this side. As they were towards downward, here also towards the base. And that is the mirage. So I hope you could understand. It appears so prominent. It is all because of the total internal reflection, where 100% of the light beam tend to reflect from the surface or from the rarer layers of air as compared to the upper part of atmosphere.